Hello. In today's lesson, we will discuss a method of measuring heat by discussing the concepts of heat capacity and specific heat capacity. These two terms will help us to measure the quantity of heat. We will first see specific heat of a substance. What is the meaning of specific heat of a substance? If I have 1 kilogram of a substance, if you notice here, I have 1 kilogram of water here. This is 1 kilogram of water. Now, how much amount of heat do I need to supply to this so that its temperature will increase by 1 Kelvin or 1 degree Celsius? You see, intervals in Kelvin and Celsius are the same. So, the amount of heat needed to raise the temperature of 1 kilogram of a substance by 1 Kelvin is called the specific heat of that substance. Alright? So, the amount of heat as a substance needs to be given to raise the temperature by 1 Kelvin. What is the unit of specific heat? It is joules per kilogram per Kelvin. The amount of heat needed to raise the temperature of 1 kilogram by 1 Kelvin. And we will represent it by lowercase c. This is brass, 1 kilogram of brass. The amount of heat needed to increase the temperature of this 1 kilogram of brass by 1 Kelvin is the specific heat of that substance. Now, experimentally, it is measured that 4,180 joules of heat is needed to raise the temperature of 1 kilogram of water by 1 Kelvin. That means the specific heat of water is 4,180 joules per kilogram per Kelvin. There you are. 1 kilogram of water requires that much of energy to raise its temperature by 1 Kelvin. Alright, you got to remember that value. That's something that we will use as we go on. 390 joules of energy is required to raise the temperature of 1 kilogram of copper by 1 Kelvin. That's right. If you got 1 kilogram of copper, you need only 390 joules to increase its temperature by 1 Kelvin. Therefore, specific heat of copper is 390 joules per kilogram per Kelvin. You see, a small amount of heat will raise the temperature of copper by a considerable amount. Now, if this is the definition of specific heat, then what is the quantity of heat, Q, required to raise the temperature of m kilogram from an initial temperature theta 1 to a final temperature theta 2? What would that be? C, the specific heat, is the amount you need to raise 1 kilogram by 1 Kelvin. So, if you multiply the mass by the specific heat and then by the change in temperature, you will get the quantity Q required to raise the temperature of m kilogram of a substance by a change in temperature of delta theta. A very important relation. Q equal to mc delta theta. Whenever the temperature of a substance is increased, the quantity of heat required to do that is given by this Q equal to mc delta theta. We will use that to solve problems, where delta theta is theta 2 minus theta 1. So, the amount of heat required to raise the temperature of m kilogram of water through a temperature difference of delta theta, Q equal to mc delta theta. Let's now define another term called heat capacity. Now, how does heat capacity differ from specific heat capacity? Heat capacity of an object is the amount of heat required to raise the temperature of the whole object by 1 Kelvin. Now, specific heat is the amount of heat you need to raise the temperature of 1 kilogram of a substance by 1 Kelvin. On the other hand, if I'm talking about the heat capacity of this object, heat capacity of this object is the total amount of heat you need to increase the temperature of the whole object by 1 Kelvin. Tell me, if I give you the specific heat of this substance, what will be its heat capacity? Well, specific heat is the amount of heat needed to raise the temperature of 1 kilogram by 1 Kelvin. Therefore, heat capacity, which I'm going to represent by the uppercase C. Now, distinguish between heat capacity and specific heat capacity. Uppercase C for heat capacity and lowercase c for specific heat capacity. If you multiply the lowercase c by the mass of the object, you must get heat capacity. Is that right? If m is the mass of an object, then the heat capacity of that object, uppercase C, will be mass times the specific heat. Is that right? If specific heat is the amount of heat per unit mass, then the total amount for the whole object will be mass times specific heat. Now, another term, molar heat capacity. Alright, can you tell me what that is? Molar heat capacity. The amount of heat needed to raise the temperature of 1 mole of a substance by 1 Kelvin is the molar heat capacity. What is the unit of molar heat capacity? It will be joules per mole per Kelvin. Joules per mole per Kelvin. The amount of heat needed to raise the temperature of 1 mole of a substance by 1 Kelvin. Alright, if m is the molar mass of the substance, then molar heat capacity C sub m, uppercase C sub m, molar heat capacity is the molar mass multiplied by the specific heat. Now, all these relations are important for you to remember. Since water is H2O, what does that mean? 2 parts of oxygen, or 2 parts of hydrogen with 1 part of oxygen. So, the molar mass of water will be the molar mass of hydrogen, which is 2, plus the molar mass of oxygen, which is 2 plus 16, that is 18, or 0.018 kilogram is the molar mass of water. So if you multiply the molar mass of water with its specific heat value, what is the specific heat value for water? 4,180 joules per kilogram per Kelvin. If you multiply that, you will get the molar heat capacity for water. There you are. Molar heat capacity for water is the molar mass multiplied by the specific heat, and that is 75.2 joules per mole per Kelvin. You need 75.2 joules of energy to raise the temperature of 1 mole of water by 1 Kelvin. Specific heat and molar heat capacity of some common substances. Now, you must print this out from the PowerPoint I have given to you and keep this with you. These are values we will be using as we move on. Very important values. Specific heat values of aluminum, copper, iron, lead, silver. Those are the common ones we use. Water. And the molar heat capacities. Okay? Alright. Let's now talk about latent heat and change of state. What does latent heat mean? Latent means hidden. Now, in this case, we are going to show that when heat is supplied to an object, when it changes its state. Now, when it changes its state, you must know that the molecular state is going to change. In a solid state, the molecules are bound together. And in order that a solid may change into a liquid, the molecules need to be free from each other. In other words, you supply potential energy to it. Now remember, an increase in potential energy will not contribute to an increase in temperature. So when you heat a substance during a time when it changes from a solid to a liquid, or from a liquid to a vapor or a gas, there will be no change in temperature, because the amount of heat supplied during that time is used to break the molecular bond to increase the potential energy. Alright, let's go and talk about this. When heat is supplied to a solid, the vibrational kinetic energy of its molecule increases, and hence the temperature of the solid will increase. Is that right? As heat is supplied steadily, the temperature of the solid increases because the vibrational or translational kinetic energy of the molecules increase, the temperature increases. Now this continues until the solid reaches its melting point. Now at the melting point, any additional heat added does not increase the kinetic energy of the molecules, but it will go into giving the molecules potential energy, or in overcoming the intermolecular forces to free molecules from one another. At this time, the solid is now changing from a solid state to a liquid state. During that time, the temperature of the solid is not increasing. This is the time when a solid turns into a liquid, a phase change. So during a phase change, there is no temperature change. During this change of state, the molecules do not speed up. If the molecules do not speed up, the temperature does not increase. But the extra energy is used in gaining potential energy. When heat is supplied to a liquid, once all the solid has become a liquid, what happens? The translational kinetic energy of the molecules will begin to increase. The temperature of the liquid will start increasing. And the temperature increases, and this continues only until the liquid reaches its boiling point. And what is happening at the boiling point? At the boiling point, the amount of energy now given to the molecules is used again in breaking the molecular bond so that the molecules become free. They fly away from each other. They gain potential energy. Again, they are used to overcome the intermolecular forces so that they can escape from the liquid to become a vapor. Right. This is the time a liquid turns into a gas or a vapor. And during this change of state, the molecules do not speed up, but the extra energy given is used in gaining the potential energy. Now, when a vapor, let's now take the journey back. When a vapor condenses to become a liquid, what happens? All the potential energy that was given earlier is going to be released. Is that right? Okay. When a vapor condenses back to liquid, heat energy is given out. That means the potential energy is going to be lost. The molecules are going to form molecular bond. So the potential energy is lost and not the kinetic energy. Therefore, there will be no change in temperature. Since the amount of heat absorbed or liberated during a change of state does not manifest a change in temperature, the amount of heat given to a substance to make it change from a solid to a liquid, or from a liquid to a gas, or from a gas to a liquid, or from a liquid to a solid, without any change in temperature, is called latent heat. It's called latent or hidden because the heat supplied or liberated does not manifest itself in a change in temperature. We will use L to represent latent heat. And what is the unit of measuring latent heat? Joules per kilogram, not Kelvin, as I have said there. You must make that, it's a big mistake there. It is not joules per Kelvin. Why is it not joules per Kelvin? Because during the latent heat, the temperature does not change. So it will be joules per kilogram. That is the unit of latent heat. Alright? The amount of heat needed per kilogram to change from one state to another is latent heat. Alright, let's now go back to our slide. Now, let's see the microscopic view of a solid. Look at this. In a solid, the molecules simply vibrate, and when you supply heat, the vibrational energy increases, the temperature increases. There you are. That's the typical solid. That's how the molecules behave in a solid. But when you supply heat, the amplitude of vibration increases. A time will come when the molecular bonds begin to break. That is when a solid melts into a liquid. And during that time, the amount of heat supplied will not manifest itself into an increase in temperature. What happens? Now look at the liquid there. The molecules can move freely within the liquid. The molecular bonds are broken. The amount of potential energy or the amount of heat absorbed during that change of state does not cause an increase in temperature. But once the liquid is formed, you give the amount of heat given now increases the vibration, the translational energy of the molecules. Is that right? And once a stage is reached or the boiling point is reached, the molecules are now ready to free themselves. There you are. They are now free. And the amount of energy absorbed to free themselves is a measure of the latent heat. And during that time, temperature does not change. That's right. They are now free to move about. Okay, let's go and define these terms one more time. What is specific latent heat of fusion? There are two types, actually there are four types of phase change. Solid to liquid is fusion. And also liquid to solid, we will also use fusion there. So when I use fusion, it is solid to liquid or liquid to solid. Vaporization, liquid to vapor or vapor back to liquid. During one stage, heat is absorbed. During the other stage, heat is liberated. So what is specific latent heat of fusion of a substance? It is the amount of heat absorbed or liberated. Absorbed when it goes from solid to liquid, and liberated when a liquid becomes a solid. By 1 kilogram of a substance at its melting point, to convert either from a solid to a liquid or from a liquid to a solid without a change in temperature. We use L sub F to represent latent heat of fusion, and its unit is joules per kilogram. And for water, this value is 333.5 kilojoules per kilogram, which is 3.34 times 10 to the 5 joules per kilogram. Write this down and keep it with you, learn it. The latent heat of fusion for water, that is, the amount of heat needed to convert 1 kilogram of ice to 1 kilogram of water without a change in temperature is this value. That means when 1 kilogram of water is converted to ice, this much of heat will be liberated. Alright, In that case, what is specific latent heat of vaporization? A similar definition, L sub V is the amount of heat absorbed or liberated. Absorbed when liquid changes to a vapor, liberated when vapor condenses back to a liquid. By 1 kilogram of a substance at its boiling point to convert either from liquid to vapor or from vapor to liquid without causing a change in temperature. And we will represent that by L sub V. And look at the value for water. L sub V for water is 2257 kilojoules per kilogram, which is 2.26 times 10 to the 6 joules per kilogram. So you must remember these three values. Specific heat of water, 4180 joules per kilogram per Kelvin. Latent heat of fusion, 3.34 times 10 to the 5 joules per kilogram. Latent heat of vaporization, 2.26 times 10 to the 6 joules per kilogram. Okay, let's now calculate the amount of heat needed to do this process. Remember, during a change of state, there is no change in temperature. So the amount of heat Q required to convert m kilogram of a solid at its melting point to liquid at the same temperature is, what will be that amount Q equal to? Mass times latent heat. It will be Q equal to m times LF, latent heat of fusion. So the quantity of heat required to convert m kilogram of a solid to liquid without a change in temperature is mass times latent heat of fusion. Similarly, if you want to convert m kilogram of a liquid at its boiling point to vapor at the same temperature, the quantity of heat required is mass times latent heat of vaporization. Alright? Okay, let's now look at some values of latent heat of fusion and latent heat of vaporization of some common substances. Again, keep this table with you. It'll be very useful in solving problems. I'm not going to go through these values. I have given it to you in the PowerPoint. Print it out and keep this with you. Now, let's review just for a second. Now, what is the amount of heat Q required to raise the temperature of m kilogram of a substance by delta theta, which will be Q equal to mc delta theta? Is that right? When there is a change in temperature, it is the specific heat that is involved there. When there is no change in temperature, what is involved is the latent heat. Now, please remember that. When there is a change in temperature, it is the specific heat that is involved. Q equal to mc delta theta. What is the amount of heat needed to change 1 kilogram of a substance to a different state without changing the temperature? That will be Q equal to mass times latent heat. Whether it is latent heat of fusion or latent heat of vaporization, depending on the change. We will be using these for our calculation. Alright, let's now go and look at more of heat calculations. Let's now heat 1 kilogram of ice at minus 50 degrees Celsius until it becomes steam at 100 degrees Celsius and see how much amount of heat is absorbed during this process. Tell me, what is the first thing that we're going to consider? We got 1 kilogram of ice at minus 50 degrees Celsius. I'm going to supply heat to that. What will happen? Ice at minus 50 degrees Celsius will increase its temperature up to where? until it reaches 0 degrees Celsius. So as heat is supplied to it, its temperature will increase from negative 50 degrees to 0 degrees Celsius. What is the equation you will use to calculate that amount of heat? There is a change in temperature, so the amount of heat Q will be, I'm going to call it Q1, that's the state 1. It's mass times specific heat times the change in temperature. Now, if you look at the table there is a value for specific heat for ice. Alright, I'm going to represent the quantities of heat at different stages on a graph. And I think if you follow this, you can solve any problems of this type. And that's equal to 1 kilogram times. Actually, there is a small change you need to make there. I'm not going to make that change here. I'm just going to say, this is ice whose specific heat is not really the same as the specific heat of water. It's slightly different. So, in this case, I'm going to leave it there. This is a measure of the heat absorbed by ice in changing its temperature from negative 50 degrees to 0 degrees, mass times specific heat times change in temperature, that is 2.09 times 10 to the 5. Ice from negative 50 degrees is now at 0 degrees. Look at that, change in temperature. Alright, as you now supply heat to this, what's going to happen? What's going to happen is, all this ice is now at 0 degrees Celsius. And this ice is now going to become water. And during the change of state, until all of the ice is converted to water, the temperature will not change. Alright, as further heat is supplied, ice at 0 degrees Celsius changes to water at the same temperature. No change in temperature. The amount of heat absorbed, Q2, is mass times latent heat of fusion. You see that? When there is no change in temperature, it is the latent heat that is involved. And what is that quantity? Mass is 1 kilogram. This is the latent heat of fusion. And that gives me the amount of heat absorbed during that stage is 3.34 times 10 to the 5 joules. How will I represent that on the graph here? There is no temperature change. Now here, all of the substance is ice, and when you come here, all of it becomes water. That is the change. So all the ice at 0 degrees has now become water at 0 degrees, taking up this much of heat, absorbing that much of heat. Alright, let's now go and see what's the next stage. Now, once all the ice has melted to become water, additional heat supplied will now increase the temperature of water until the water temperature reaches 100 degrees Celsius. So, what is the quantity of heat absorbed during that time? Q3 equal to mc delta theta, where m is the mass, 1 kilogram, c is the specific heat of water, and delta theta is the change in temperature. That will be 1 kilogram times specific heat is 4180 times delta theta is 100 Kelvin from 0 to 100. And that is 4.18 times 10 to the 5 joules. Now, where will I show that on the graph? Water at 0 degrees now become water at 100 degrees. This is the quantity of heat during that time. This is the amount of heat. So Q3 equal to mc delta theta. And finally, we're going to boil away all this water to become vapor. So here, the water is now at 100 degrees Celsius. What happens when you supply additional heat? As further heat is supplied, water at 100 degrees Celsius changes to steam at the same temperature. There is no temperature change, and therefore we now have latent heat of vaporization. The quantity of heat Q4 equal to mass times latent heat of vaporization. Mass is 1 kilogram. Latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram. And that gives me 2.26 times 10 to the 6 joules. And where will I represent that? There. That represents Q4 is mass times latent heat of vaporization. If I now want to calculate the total quantity of heat absorbed by ice at minus 50 degrees to become vapor at 100 degrees, you've got to now add all these. You see that? Q1 is MC delta theta, change in temperature. Q2 is MLF, no change in temperature, latent heat. Q3 is MC delta theta. And Q4 is MLV. If you follow this pattern, you can solve any problems in calorimetry. I'm going to show you what calorimetry is. Let's do a simple problem. A solar home contains 10 to the power of 5 kilogram of concrete of specific heat capacity 1 kilojoules per kilogram per Kelvin. How much heat is given off by the concrete when it cools from 25 to 20 degrees Celsius? Now, the first thing you notice that there is a change in temperature, so the equation will contain the specific heat. Mass is 10 to the power of 5 kilogram. Specific heat is 1 kilojoules per kilogram, 1000 joules per kilogram per Kelvin. And delta theta is 5 Kelvin. Therefore, the quantity of heat given off is mass times specific heat times change in temperature. Now use all those values, what do you get? That is 5 times 10 to the 8 joules. This is a very good way of heating homes. You can actually heat when electricity is abandoned, say during some off-peak time. You can heat a very big pile of concrete and then leave it in the house so that the heat will be radiated to heat your homes. Alright, think about it. Okay, this is the same as 500 megajoules, is that right? 500 times 10 to the power 6. Let's now talk about the principle of calorimetry. Calorimetry is the science of measuring heat. Now, what is the principle of calorimetry? When hot objects are mixed with cold objects, we will actually do experiments in the lab by mixing hot objects with cold objects. Now, what happens? Hot objects will lose heat, cold objects will gain heat. And if you perform the experiment in an insulated environment and allow thermal equilibrium to reach, what does that mean? It means the hot objects will lose heat, cold objects will gain heat, and there will be an equilibrium. And when the equilibrium is reached, total heat lost by hot objects will be equal to the total heat gained by cold objects. Now, that's the principle of calorimetry, and we're going to use that to solve problems. And in order to do that, we will be using something called a calorimeter. This is a calorimeter. And the experiment will be done inside. This is actually the calorimeter. This has to be insulated from the surroundings. That's why it is kept inside there. And we will allow heat exchange to take place inside the aluminum container. So you have a calorimeter where calorimetric measurements are done. Okay. Now this principle can be used to solve for unknown quantities. And what we're going to do the rest of the time for this lesson is to solve problems like that. Let's look at this problem. How much heat must be removed when 100 gram of steam at 150 degrees Celsius is cooled and frozen into 100 gram of ice at 0 degrees Celsius. Specific heat of steam, C sub S, is this. If you notice this, this is the reverse process of what we did earlier. Earlier we took ice at minus 50 degrees Celsius and heated it until it became steam at 100 degrees Celsius. Here I have steam at 150 degrees Celsius. It's going to cool down to become ice at 0 degrees Celsius. Let us trace the various parts. Okay, mass is 0.1 kilogram. Specific heat of steam is 2010 joules per. Now always what's the unit given? 2.01 kilojoules per kilogram is 2010 joules per kilogram per Kelvin. And this steam is first going to lose its temperature from 150 degrees to 100 degrees. So in stage 1, steam is going to cool down from 150 degrees to 100 degrees. The change in temperature is negative 50 Kelvin. Negative indicates that it is losing heat. So steam at 150 degrees cools down the steam at 100 degrees Celsius. What is the quantity of heat liberated? A change in temperature, mass times specific heat times change in temperature. We know all these values. So mass is 0.1 kilogram. Specific heat is given. The change in temperature is given. Now I haven't used the negative sign here. The negative sign simply tells you that heat is not absorbed but liberated. So we will only find the magnitude of it. That will be 1.01 times 10 to the 4. Now I warn you, you need to do all this on your own. Okay? Either along with me or after you listen to the lecture. You can pause the lecture anytime you want and work it out and then continue. Alright, let's do it on a graph. Can you show me where will this appear on the graph? Now this is where the steam is going to start at 150. So it starts at 150 and cools down. Now I've started from the right to the left because the quantity of heat is given out. Alright? The quantity of heat given out is mc delta theta 1.01 times 10 to the 4. What is the next stage? Water at 100 degrees Celsius is going to, no, this is steam at 100 degrees Celsius. All that is now going to condense to water at the same temperature. There is no temperature change. So steam at 100 degrees Celsius changes to water at 100 degrees Celsius. Can you tell me what is the quantity of heat this time is? Q2 is mass times latent heat of vaporization. That's the mass, that's the latent heat of vaporization. That gives me 2.26 times 10 to the 5 joules. Where will I represent that on the graph? There is no temperature change, so it will be a horizontal line. All the substance here is steam, and after losing this much of heat, all the substance now become water, change of state. And now you have water at 100 degrees is going to cool down to water at 0, change in temperature. Is that right? Let's go there. Water at 100 degrees Celsius cools down to water at 0 degrees Celsius. The change in temperature, the quantity of heat is mass times specific heat times change in temperature. Let's put those values there. And that is 4.18 times 10 to the 4 joules. Where will you represent that? There you are. So that will be 4.18 times 10 to the 4 joules. What is the next stage? We've got to convert all the steam to ice at 0 degrees Celsius. So we have now reached water at 0 degrees. All that water has now to become ice at the same temperature. So water at 0 degrees freezes to ice at 0 degrees Celsius. The quantity of heat given out will be Q4 is mass times latent heat of fusion. Alright, 0.1 kilogram latent heat of fusion, that is 3.34 times 10 to the 4 joules, and there you are. So we started with steam at 100 degrees Celsius, and we are now back with ice at 0 degrees Celsius. How much is the amount of heat given out altogether? The total amount of heat liberated is the sum of all these, and I got it as 3.113 times 10 to the power of 5 joules. Alright? If you are familiar with this method, you can really solve any problem. Let's do another one. If 500 grams of molten lead at 327 degrees is poured into a cavity in a large block of ice at 0 degrees Celsius, how much of the ice melts? You got to understand the problem first. You got molten ice poured into a block of ice. Now what's going to happen? The molten lead, first of all, is going to liberate heat to become solid without changing temperature. Then the solid lead is going to lose heat to cool down to 0 degrees, losing an amount of heat. Now, who is receiving all that heat? All that heat lost is being absorbed by ice at 0 degrees to become water at 0 degrees. Is that right? Okay, so there is receiving and giving. We would say the total heat given out by lead equal to the total heat absorbed by ice. All right, let's do that. Molten lead becomes solid lead at the same temperature. Is that right? Liquid freezes to solid without changing temperature and cools down to 0 degrees Celsius, giving up heat. An m kilogram of ice, we don't know what m is, we need to find m. M kilogram of ice melts by absorbing all that heat. Alright, let's approach graphically as before. What is the first step? Molten lead at 327 degrees Celsius becomes solid lead at the same temperature. What is the quantity of heat given out? What is the equation? Can you write down that equation now? Q1 equal to mass of lead times latent heat of fusion. Latent heat of fusion for lead is given. So that will be 0.5 kilogram times latent heat of fusion. How much is that? That is 1.235 times 10 to the 4 joules. Can you represent that on the graph? There you are. Here where I'm pointing, all the lead is melted. This is melted or liquid lead at 327 degrees Celsius. And all that liquid lead is now solid lead here, giving out that much of heat. Or this is the amount of heat given out. And now what's going to happen is lead at 327 is going to cool down to 0 degrees Celsius. Alright. Lead at 327 degrees Celsius cools down to 0 degrees Celsius. There's a change in temperature. Therefore, the quantity of heat given out is mass times specific heat times change in temperature. And we know the mass, we know the specific heat of lead, I gave it to you. 0.13 times 10 to the 3 is 130 joules per kilogram. Times the change in temperature is 327 Kelvin. And that is 2.126 times 10 to the 4 joules. And this is the amount of heat given out. Lead at 327, is that right? At 327 degrees, cool down to 0 degrees, giving out that much of heat. And now, this is the total amount of heat given up or liberated by lead. What is the total heat lost by lead? Is Q1, this Q1 plus Q2, and you add them together, I got 3.361 times 10 to the 4. I want you to check this on your own. Okay, this is the total heat given up or liberated by lead. Now, who is absorbing all that ice? All that steam. All that steam is being absorbed by m kilogram of ice simply to melt. That is, change from solid to liquid without change in temperature. So, we've got m kilogram of ice melts by absorbing all this heat. Now, what is the heat absorbed by ice? What is the heat absorbed by m kilogram of ice to change to water without changing the temperature? It's mass times latent heat of fusion. And now, this quantity should be equal to the amount of heat given out by lead. Well, this is m kilogram times latent heat of fusion for ice is this value. And that will be, I wrote it like this, 3.34 times 10 to the 5 m. You don't know m. Alright? And I represented that by the blue line. Here, we got all that m kilogram is ice here. And over here, all that m kilogram is water. So all that m kilogram of ice has now been converted to water. Heat is absorbed by ice, and all that heat absorbed is actually come from lead. Alright? So, heat lost by lead, that quantity, equal to heat absorbed by ice, that quantity. There you are. Now, you can solve for m. What is m equal to? M equal to this quantity divided by that quantity, and that is 0.1 kilogram. You can see, because the very high value of latent heat of fusion, all this heat given out by lead only melts 0.1 kilogram or 100 gram of ice. Alright, that was a neat problem. Let's do another one at the same time. A well-insulated bucket, like the calorimeter I just showed you, contains 150 gram of ice at 0 degrees Celsius. A, if 20 gram of steam at 100 degrees Celsius is injected into the bucket, what is the final equilibrium temperature of the system? Is any ice left in the water, not ward? It should read as water. Is any ice left afterward? I'm sorry, my fault. Is any ice left afterward, after doing this process? So what do you have? A well-insulated bucket contains 150 gram of ice at 0 degrees Celsius. And we're going to inject this much steam into steam at 100 degrees Celsius into that ice. The question is, will all the ice be melting? And if so, what is the final common temperature? Or is there any ice left? How do we start it? First of all, picture this problem. Steam at 100 degrees Celsius first condenses to water, releasing a quantity of heat without change in temperature. So steam at 100 degrees Celsius is going to change to water at 100 degrees Celsius without changing temperature. The quantity of heat released will be mass times latent heat of fusion. And mass is 0.02 kilogram, 20 gram, and latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram. And that is equal to this quantity. Let's put it on a graph. Where will you draw that? Well, this is where we start. And what do we have? Steam at 100 degrees condenses to water at the same temperature. That means there's no change in temperature. We started with steam here, and all of that steam becomes water here, releasing this much amount of heat. Alright, now what happens? Water at 100 degrees is going to come down to some common temperature, and I have assumed that let the common temperature be theta. So, water at that 100 degrees is going to cool down to theta, assuming that all the ice melted. We made an assumption here. Let's assume that all the ice melted and the temperature of the melted ice increased to theta. And that's the common final temperature. Alright, if theta is the equilibrium temperature, this water at 100 degrees Celsius cools down to theta degrees by releasing an amount of heat. Now, how much is the amount of heat released by water? Can you write down that equation? Q2 equal to mc delta theta, mass of water times specific heat of water times change in temperature. What's the mass of water? 20 gram. Specific heat of water is 4180. The change in temperature is 100 minus theta. And so that will be, I calculated that, I got 83.6 times 100 minus theta, and that is the part on the graph. Water at 100 degrees Celsius cools down to theta degrees Celsius, losing this much of heat. And now, what's the next step? Let's now start with ice. Ice at 0 degrees first melts to become water at 0 degrees. Assuming that all the ice melted, this ice at 0 degrees melts to become water at 0 degrees. What is the quantity of heat absorbed by that ice? There's no change in temperature, it's the latent heat. Q3 is mass times latent heat of fusion. And the mass of ice is 150 gram, 0.15 kilogram. Latent heat of fusion is 3.34 times 10 to the 5. And that is 5.01 times 10 to the 4 joules. Alright, so this is ice at 0 degrees. All that ice has now become water at 0 degrees, absorbing an amount of heat 5.01 times 10 to the 4. Now, what is going to happen to this water, this melted water? Its temperature is now going to increase from 0 to theta. There you are. Water at 0 degrees is now going to heat up to theta degrees. What is the amount of heat absorbed by that? Q4 is mc delta theta. I hope by now you know when to use mc delta theta, when to use mass times latent heat. When there is a change in temperature, it is mc delta theta. When there is no change in temperature during a change of state, it is mass times latent heat. Alright, we know the mass, we know the specific heat of water, and the change in temperature from 0 to theta is theta minus 0. And that's equal to 627 theta. Is that right? Yes. So it will be this part. Water at 0 degrees warms up to water at theta degrees. The amount of heat absorbed is 627 theta. Now, you have a certain amount of heat absorbed by ice, that's the red line, and a certain amount of heat lost by the steam, the green line. The total amount of heat lost equal to the total amount of heat absorbed. Let's do that next slide. Total heat lost by steam is this quantity plus this quantity. There you are. And the total heat absorbed by ice will be this quantity plus this quantity. 5.01 times 10 to the 4 plus 627 theta. And now we can equate the two, because the principle says the amount of heat lost equal to the amount of heat gained. So we have this whole quantity equal to that. And what is all left for us is to distribute that quantity and group terms containing theta and solve for theta. I can do that, I can leave that for you. But you can see I have distributed that, give me this. And then I combined the terms in theta on the right side and combined all the other terms on the left. And then the numbers on the left, if you use your calculator, simplifies to 3,460. And on the right, 83.6 theta plus 627 theta is 710.6 theta. And that gives me theta equal to 4.87 degrees Celsius. Now, this is a beautiful problem, and you must know how to solve problems like this. All right? And since the equilibrium temperature is greater than 0 degrees Celsius, there is no ice left. Let's do one more problem. A calorimeter of negligible mass contains 1 kilogram of water at 303 Kelvin and 50 grams of ice at 273 Kelvin. Find the final temperature T. This is almost the same principle. Alright? Ice at 273 Kelvin melts to become water at 273 without changing temperature, absorbing an amount of heat, Q1 equal to mass times latent heat of fusion. Mass is 0.05 kilogram. Latent heat of fusion is that quantity. Therefore, the amount of heat absorbed by ice is 1.67 times 10 to the 4 joules. And how do I draw this? There you are. Now here is ice at 0 degrees, and after absorbing this much of heat, it becomes water at 0 degrees. The amount of heat absorbed. Now water at 273 is now going to warm up. You see, we assume that the common equilibrium or the final temperature is T. So this water has to now warm up to T. So water at 273 Kelvin warms to become water at T Kelvin. What is the amount of heat absorbed? There's a change in temperature, so that will be Q2 is mass times specific heat times change in temperature. And that will be mass, specific heat of water. The change in temperature is T minus 0, and that will be 209 times T minus 273. And it will be represented here. Water at 0 degrees becomes water at T degrees, absorbing an amount of heat by this quantity, 209 times T minus 273. And what's going to happen to, now, where does all this heat come from? Now, this is the total heat absorbed by ice. That's there. Now, water loses heat in cooling down from 303 Kelvin to T Kelvin. All this heat is going to come from this water. How much is the heat lost by water in cooling down from 303 to T Kelvin? It's mass times specific heat times change in temperature, and that would be 1 kilogram times the specific heat times the change in temperature from 303 to T. And that will be, I distributed that, this big number minus 44,180 T, And that will be here. Water at 330 now cools down to T. There you are. Now total heat absorbed equal to total heat lost. Total heat absorbed equal to total heat lost. There you are. And now it is simple for you. I'm going to leave it for you to combine the terms in T and solve for T. So T equal to 297.8 Kelvin. Now, this is a relatively easy part of thermodynamics. So I went a little fast. I want you to go back and do all these problems. Now, do all the homework. Make sure after watching every lesson, you do all the homework. Alright? I'm going to stop this here. I'm going to continue with the next lesson later on.